All right, so we're going to take a look now at some of the topics from the acids and bases section. And one of the first ones we're going to take a look at here has to do with how we identify acids and bases by how they react with water. So remember, as a general rule, acids are things that when they dissolve in water, they produce the hydronium ion, H3O+. And bases are things when dissolved in water produce the hydroxide, OH-. So in this example, we're going to be looking to see what, based on the types of species that are present in aqueous solution, we need to decide, and what the compound is, we need to decide whether that compound is ionic, whether it's molecular, whether it's a strong or weak acid or strong or weak base. So let's take a look at the first one. So we have HF is our compound. Okay, and right away we can see that they're only non-metals. Okay, so we're using some info from the previous chapters. This means that this will be molecular or covalent, because there aren't any metals in there. So it's not ionic. If there was a metal, we would right away think ionic. This is also telling us that when dissolved in water, the important species are the following. So we have H3O+, we have F-, we have HF, and then we also have H2O. All right, so H2O is always going to be present because it is the solvent for the aqueous solution. So here it's telling us we have H3O+. So right away we know that it's an acid because we produced some of that. So the question then is it a strong or weak acid? Well, we can look at the other species present to see whether or not we have any of this original compound left over. So if you see any of this original one left over, like it is here, right? So you still have some of this present. That means that this doesn't break apart completely in solution. There's some of this left behind. And because there's some of it left behind, it doesn't dissociate completely to give you these ions here. Some of it's left behind, so then we know that that is going to be weak, right? And that's the definition of strong versus weak. Acids and bases, strong acids dissociate completely. Weak acids do not dissociate completely, so we're going to see a little bit of the original compound left. So this first one here is going to be molecular, and it is also a weak acid. All right, if we take a look at maybe the Ba barium hydroxide, BaOH2, that's this one, we can see that the species present, we have the barium ion, we have the hydroxide ion, and then we have water. All right, so right away, we're seeing a metal in there, so that means that this should be ionic. We're seeing that we have the hydroxide present, so that means that this is a base. Do we have any of this original compound remaining in our, when it's dissolved in water? No, so that means then that this entire thing breaks apart completely. So this is going to be not just a base, but a strong base as well. All right, so that's how you want to go through and interpret that table. All right, let's take a look at identifying now Bronsted-Lowry acids and bases. So the Bronsted-Lowry is another definition that we use to describe acids and bases. And this has to do with their behavior based specifically on their ability to either lose or gain a proton. So acids are things that donate, lose, or give up protons, which remember are H+ ions. And bases are going to do the opposite. These are going to accept H+ ions, right? So the Bronsted-Lowry definition just looks at what's happening in terms of H+. So let's take a look at the first one. So decide whether the highlighted reactant is a Bronsted-Lowry acid, Bronsted-Lowry base, or neither. So if you take a look at the NH4 plus OH-, producing NH3 and H2O, right? So this is the thing we're concerned with here. So what you want to do is you want to try to find something on the other side of the reaction that kind of looks really similar to the species in question. And the one that looks similar to it is the NH3. All right. So what's happening when the NH4 plus becomes the NH3? Well, in this case, it has to lose. It has to give up that H plus. Right? So if you take away an H from this, you end up with NH3 plus, but then you're also taking away an H plus, right? So if you take away this positive charge, you end up with something that's neutral. We reduce the number of H's by 1, so we end up with an H3. Because it loses an H plus, then this is going to act as a Bronsted-Lowry acid. So as you go through this table, that's what you want to look at. Look at the species in question, see what else on the other side is kind of looks similar to it. So let's do the other one that's right beneath it. So in the second one here, we're looking at the OH minus. Okay, and what on the other side kind of looks similar to it? Well, that's the H2O. So in this case, in order to get from OH minus to H2O, we need to add or accept an H plus, right? So now we're going to have two H's. And then we're also adding a positive charge to this, so it'll cancel out the negative to give us a neutral. We end up with water. So because this is accepting an H plus, this is going to act as a Bronsted-Lowry base. That sort of ties into the next question that deals with the conjugate acids and bases. So conjugate acid base pairs is what we're looking at. So if we're looking at an acid, and this is based again on the Bronsted-Lowry definition, acids are going to do what acids do, which is to lose an H plus or give up an H plus. Then what it becomes is the conjugate base. Okay, and that is the connection between them. And this conjugate base has one fewer H. And the other thing that happens is the charge is going to become more negative. Because we're not just taking away an H, we're taking away an H plus. All right, so let's take a look at the, let's do the one down here, NH4 plus. So we're saying if NH4 plus is acting as an acid, we're going to lose an H plus from this. So it's going to have one fewer H. So instead of having 4 H's, it's going to have 3 H's. And the charge now becomes more positive. Specifically, it's going to reduce by one positive charge because we're losing an H plus. So we take away the positive. This then ends up with a neutral charge. And we actually saw that in the question above here. All right, so conjugate bases have one fewer proton, and the charge becomes more negative by one negative charge. And then the opposite would be true when we look at if something is acting as a base, it is going to accept an H plus. It becomes a conjugate acid, and the conjugate acid would have one more proton, or one more H, and then the charge becomes more positive because we're adding not just an H, but an H plus on there. So for instance, if you look at this middle one here, the ClO3 minus, which is the chlorate ion, if this is acting as a base, it is going to accept an H plus. So we're going to stick that H here at the front. So HClO3, nothing else changes. Right? All we're doing is we're adding an H here to it. And we're adding not just an H, but an H plus. So obviously the positive charge will cancel out the negative charge to give us a charge of 0, right? So here the charge does become more positive. It goes from -1 to 0. All right, let's take a look at the next one. So we're taking a look at predicting the products of the reaction of a strong acid with water. Okay. And we have here our HI, that's aqueous, combining with H2O, liquid. Okay, so we're saying that this is a strong acid Well, what do strong acids do? Well, they give up that H plus. Where is that H plus going to go? Something has to accept it. The only other thing there is going to be the H2O. So if we stick an H2O, I'm sorry, an H plus onto an H2O, end up now with 3 H's and O, and we didn't just put an H, we put an H plus. So that's going to have a positive charge. That's the hydronium ion, now dissolved in aqueous solution. And then if we take away an H plus from this thing, we end up with I minus. That's also in aqueous solution, right? So we're taking this here and we're splitting it, right? Because acids are going to do what acids do, donate H plus. And the conjugate base of this ends up being I minus. H plus goes and it grabs a hold of the H2O to make the hydronium ion. And then this makes sense because if this is acting as an acid, it is going to produce the hydronium ion. All right, so let's take a look at the next one. So when we get into some of the calculations. So we have here an aqueous solution at 25 degrees. The temperature really doesn't have anything to do with this. All we do, we need to specify the temperature because pH is temperature dependent. So it tells us that the pH is 6.88. And it says calculate the pOH. Be sure the answer has the correct number of sig figs. Okay, so we have the pH, we need the pOH. And there's a very simple relationship between the pH and the pOH at 25 degrees, and that is the pH plus the pOH is always equal to 14. So if I need the pOH, all I need to do is to take 14 and I subtract the pH, and we know what the pH is, 6.88. And then that's going to give you whatever you end up with. All right, so that's a fairly simple case of subtraction. You just need to know this relationship. All right, so here we have interconvert. The next one was interconverting hydronium and hydroxide concentration at 25 degrees Celsius. And again, the temperature is just specified. So it says the concentration of hydroxide. So remember, square brackets mean concentration of 1 times 10 to the negative 7 molar. And we need to calculate the H3O plus concentration. All right, and here again, we need a relationship between these two, and the relationship is the KW relationship, or the ion product, and that product is a constant. So if I multiply the concentration of the hydronium by the hydroxide, I always get a number, and that number doesn't change, so it's a constant, 1 times 10 to the negative 14. So if I need to calculate the H3O plus concentration, I'll take the 1 times 10 to the negative 14, I divide it by the hydroxide. So I know what that is. I'm going to just substitute it now into my equation. All right, and here you'll need to make sure that your calculator skills are up to par. How you enter these numbers, usually use parentheses to separate them, and then you'll see that this ends up being 1 times 10 to the negative 7 as well. All right, so whatever your hydroxide is, whatever that concentration, just stick it into this rearranged equation. All right, so let's see. The next one looks at interconverting pH and hydronium. Okay, so let's look at A for right now. So it tells us that for solution A, the concentration of the H3O plus is 7.3 times 10 to the negative 9 molar, which is the same as moles per liter. So the pH of that solution is simply, we take the negative logarithm of the concentration of the H plus. Okay, so you need to type this into your calculator as written, and depending on what type of calculator you have, the way that you enter it may be slightly different. So if you plug that in, you'll see you end up with you'll end up with 8.14 as your pH, and this being more than 7, this would be a basic solution, right? So you really need to make sure that you can type that into your calculator and evaluate the pH of your solutions. Let's take a look at the second one that's going in the opposite direction. So in the second one, we're actually given the pH as 7.38, and we need to find the concentration of the H3O plus. And this is just working with logarithms in the reverse direction. And the H3O plus here is simply 10 raised to the power of the negative pH, right? So we have 10 raised to the power of negative 7.38. And you have to evaluate that. So because you need a number, you can't just leave it in that way. So again, using your calculator, so we have 10 to the negative 7.38. And that would give you, let's see here. We have 4.2 times 10 to the negative, we got 1, 2, 3. Negative 8 molar. So again, your calculator skills are going to be very, very important in this section. And then the last one looks at identifying strong versus weak acids and bases from our sketch. So this relates directly to the one that we looked at up at the very beginning, where you were asked to identify the species present in solution. Now we're taking a look at a sort of a diagram. All right, so so remember what we said about strong versus weak acids and bases. Whoops. So a strong acid is one that dissociates completely to give you the ions present in solution, and you're also going to have water. A weak one is going to have some of the original acid or base left over, right? So for a strong base, if we slide here, well, you can't see it on mine, but that's what you want to look at to identify whether the sketch is correct or not, right? So if you're dealing with a strong base, okay, this is going to dissociate completely. So for example, if I have something like sodium hydroxide, okay, this will break apart. I'm going to get lots of Na plus, and I'm going to get lots of the hydroxide. And then being in aqueous solution, I'm always going to have some water as well, right? And that's all that I'm going to see. If I have a weak base, it does not dissociate completely. And that means you're going to have some of the original left over. So for example, in the case of, if you look at ammonia, in solution, ammonia actually forms the NH4 plus. We're going to get some hydroxide as well, but then we also have some of the ammonia that stays on its own, and then we're going to have some H2O, right? So you'll notice that we do have the hydroxide, but we still have some of this left over, and that's really what you're looking at to see whether it's strong versus weak. In the strong example, we don't have any of the sodium hydroxide left over. It's completely broken apart into the sodium and the hydroxide.